Welcome to the course on Scalable Data Science. My name is Anirban and I am from IIT Gandhinagar. So today's lecture is going to be on feature hashing. So until now we have studied applications of both sampling and random projections to a bunch of optimization problems relating to linear algebra, right? We first saw applications of random projections to this low rank approximation of at least two different forms, to matrix multiplication, to L2 regression, and then in the last lecture we also saw how we can turn some of these, how we can also employ sampling to solve some of these problems, right, using the leverage score sampling techniques. So a lot of these, one big thing that is missing, while a lot of these is relevant in unsupervised machine learning, right? The supervised is a slightly different ball game. Okay, and in this lecture we'll explore how random projection and related techniques can also be useful in supervised machine learning. Right, the basic techniques and the intuition is going to be the same. Right, the problem is going to come from that of supervised machine learning. Therefore, and what we'll discuss at the end is what a new kind of guarantees should we hope to have in this case. So let me give the outline first. There are going to be two different use cases, both of them relating to text. In one use case, what we'll consider is that there's going to be a very large feature space, right? And we'll point out why having a large feature space is actually useful. Essentially, it's going to be to capture very long range correlations in my document, in a specific document. And we'll have to come up with some technique to control the size of this feature space, right? And I mean, having a large feature space is actually useful for classification. However, I mean, is actually useful in improving classification accuracy. However, it is computationally very inefficient. Therefore, what we'll do is that first we'll pose the problem as having a large feature space, and then we will use random projection to cut down the feature space while preserving the benefits, some of the benefits that we had brought in because we introduced a large feature space, right? So in this way, we'll sort of, do both, right? A similar story is going to come out in Mayer's classification. Here what we are going to say is that we have to introduce a large feature space in order, as a cheap way of trying to give personalized classifiers to each individual user. Okay, and again this is going to blow up the entire problem size by a lot, right? And therefore we are going to use random projection related technique to cut it down. Right, and what we will see in both these settings, a very specific type of random projection is going to be more useful to us. Okay, so let me outline the two use cases first. So in the text classification setting, right, let's think about what kind of classifiers work best. Right, while nowadays you see a lot of this nonlinear, non-convex classifiers, the deep neural nets that give excellent results in speech and vision. Right, there's a typo out here, and these are good because they have very high accuracy. They are also reasonably fast at test time. However, during training time, they can be terribly slow, right? And often they require a lot of thinking and a lot of domain expertise in order to ensure that you don't get stuck in bad local minima. Right? There are a lot of heuristics that you need to know about. Furthermore, it's not clear that a lot of these these non-convex classifiers are very useful when the data is sparse and high dimensional, right, i.e. when the data comes from text. Right? Although there are techniques like word2vec that are changing this, that are creating dense representations of of sort of very sparse documents and words, and thereby using it. However, it's still not clear that they can beat the very practical systems that are robust, right? That are formed by much simpler means. Okay, so in practice, what is still very useful are what I call count-based features, right? And these slides are actually from a talk by John Langford. Okay, so in essence, what I mean is that I mean, if you remember the normalized or rather the bag of words model of a document, right, in which you essentially represent a document as a set of its tokens along with the counts that are associated with these tokens, and these counts could represent some normalized term frequency, inverse document frequency, things like this. So you could come up with the normalization with the term count in very fancy ways. Right, we could take this bag of words model and we could augment it quite a bit. Right, so the benefit of this simple bag of words model is that it's fairly easy to train, at least on a single machine. Okay, and parallelization is a different ball game altogether. It's also clear that it's fairly fast at test time, right? Because all you need to do is essentially compute some statistics from this from the query document and then use that for prediction. Right, and it turns out that this still works surprisingly well for text classification, right, which still forms a large part of the machine learning, or the practical machine learning tasks that we do. Right, and a common practice, I mean, if you want to augment the naive bag of, if you think that the bag of words model itself is naive to start with, a common practice to augment it is to take various combinations of engrams and skipgrams. And the intuition is that if I take if I take bigrams, trigrams, etc., and skipgrams, we'll be able to capture high-level correlations. But still, they are fairly efficient to calculate, and therefore we are capturing the high-level correlations while retaining the efficiency of feature construction. Okay, let me give an example of bigrams and engrams. So, for instance, here is the sentence that we have: the rain in Spain falls mainly on the plain. Okay, so the 2 grams so of course the unigrams in this particular document would be the individual words. The rain in Spain falls mainly in the plain. Right, the 2 grams would be the rain in Spain, Spain falls, etc. And what you can easily see is that by looking at the set of unigrams, you're getting a better idea of what the document is about. So that the skipgrams that I just mentioned has different variants to it. Right, here is one particular variant that is known as a 1 skip 2 gram. Right, that is, you take bigrams, right, where between 2 bigrams that you take, you just skip one of the bigrams. For instance, you take the and in. Right, similarly you take rain and Spain. Right, you take in and false, and so on and so forth. Right, and the point is that if you take a number of such variations of this 1 skip 2 grams, 2 skip 3 grams, and so on and so forth, you essentially capture this collection. So first of all, these set of features are trivial to automatically construct. You're not sitting down and thinking about special feature engineering. And secondly, once you throw in all these features, they actually capture a lot of semantics of the document. Right? An interesting way of looking at this is that if I sort of take a representation of the document in this bloated up feature space and then calculate the similarity of this, you can also think about it as some kind of kernel representation of the document. Right? Essentially, instead of a simple features, we're taking combinations, 2 combinations, 3 combinations, 4 combinations of these features. The only problem that I see right now is that all these are good, but the feature space is becoming very high dimensional. For instance, if you take a few variants of this unigrams, trigrams, and then 1 script 2 grams, and so on and so forth, then the number of possible features becomes, let's say, if it's a 3 gram, it becomes the cube of the size of the English dictionary, which is a lot. So how should we deal with this? Okay, so for the second example, let us look at the problem of mail classification, right? And here's the problem: that suppose a piece of mail comes to us, right? And now we have to decide whether to put it in a particular user's inbox or in the spam box. Okay. Now there are different and in order to do this, all the standard online email systems. So think of a webmail system have their own classifiers that they have trained, right? And these classifiers, based on their decision, they put it in they decide to put it in the inbox or in the spam box. And now the classifier also gets feedback from the users, right? So the user can possibly read, reply, forward, delete, forward, and then or she could delete or mark the user as spam, right? So it's possible that I take these as the positive feedback and these as the negative feedback on the email, right? And based on these feedback, I can retrain my classifier, Okay, so the things to keep in mind is that each email needs to be classified in the spam box or inbox, and therefore this has to be done in basically real time. Classifier has to be updated by user feedback, which means that it has to be updated frequently, because the nature of spam keeps on changing and users don't always agree about what is spam, right? So in machine learning terms, this is in order to satisfy those requirements, this is what we have to do, right? So suppose we are representing each email as a point in some high dimensional space. So these are the emails, these points are the emails, okay? And now and every user's classifier representing as a vector in this high dimensional plane, right? Users 1's classifier, users 2 classifier. So first I said that users have different spam preferences. So what it means is that the classifier for each user is slightly different, right? So user 1 can potentially consider the emails from Groupon and Yahoo to be spam, but maybe user 2 considers this company, this is a company called Target, and Yahoo to be spam, but not Groupon. Okay, so we need to assign different classifiers to each user, which means that we need to store a different hyperplane for each user. Okay, we also need to ensure, at the same time, we also need to ensure that new users get a good classifier, right? Because for new users, we don't have that many feedback from the user, but we still need to guarantee that we get a reasonably good classifier for the user, right? Furthermore, we want to update this classifiers frequently using new feedback. Okay, so how can we achieve all these? So here is one particular very interesting way of doing all this. What we do is that we say that let us blow up the feature space, right? And how do we blow up the feature space? Let us take the email, right? And we do a sort of standard bag of words or unigram or bigram decomposition, and we get these unigrams or bigrams from the email, right? Now in order to sort of now what we do is that in order to we assign every user their own feature address space, right? What it means is that the global set of features, this global set of features, and then there is a set of features that belong to user 1, then there is a set of features that belong to user 2, belong to user 3, and so on and so forth. So this is global set of features, right? And how do we implement this? We implement this very simply. We take all the tokens, right, and then we take all the tokens by themselves. These belong to the global feature space, right? We just prefix the name, the token by the name of the user, right? And these then belong to the user specific feature space. So notice that only the emails that U1 gets, right, that belong to U1 will have tokens that are specific to U1, right? The emails that the same email if U2 gets, it won't have this particular token, right? Because it is prefixed by the user 2's, it's going to be prefixed by the user 2's name, not by user 1's name. Okay, and now what we'll do is that we say that let us learn a classifier on this entire feature space, right? It's not very hard for you to see that what this corresponds to is that for every user we are learning a classifier of the following form. A classifier which has a component in the global, a set of coefficients for the global feature space, and a classifier which has a set of coefficients for the user feature space, right? So therefore, for a particular email, for a test email, right, what the classifier does is as follows: that it takes let me call this W global. This is W global, and the set of coefficients here to be W user, right? So therefore, for a test email, we again do a sort of representation of the email in the global space and in the user space, and then we take the corresponding dot products. And therefore, what it turns down to is that we sort of and we could apply a threshold on this, and therefore what it says is that we are combining a global classifier with a user specific classifier, and we are giving a particular user the combination of these two classifiers. Right? It's entirely possible that, so why is this good? This is good because consider a particular user who has just come into the system. So for that particular user, the W transpose user is 0, right? Because I have not yet trained a user specific classifier, because the user has not given any feedback, right? Therefore there won't be any token on the user specific part. Okay. So but for this user we still have the global component, right? And we are still and because that is trained by everybody's feedback, right? That's a reasonably good classifier. It's not clear, it's not very tailored to that user's needs, but it's fairly good. Okay. So therefore, if I start off this new user with this global classifier, she has a reasonably good experience. And thereon onwards, this particular user can start providing feedback if she wants to, and therefore the value of this, the importance of this part of the classification technique increases, and so there might come a time, if the user provides enough feedback, that this part of the classification really has more importance than this part, which is the global part, and then the user will start sort of acquiring the benefits of personalized classifier. Okay, so this is a very natural way of going from a global initialization to a personalized classifier for more involved users. Okay, what is the bad thing about it, right? An obvious bad thing about it is that the size of the resulting dimension space has blown up a lot, because if you imagine that if I have n users, right, if d was the size of my initial dictionary, my current set of dimensions is n times d. Right, because I'm multiplying the user by I'm multiplying the number of possible the size of the possible dictionary by the number of users. Okay, and this is potentially huge, right? Because while the emails are sparse, the vectors w and are sparse. So therefore, keeping all these vectors w in this maintaining this vector w in this particular space is fairly expensive. Right. So maintaining even a single w, which is what you really have to maintain in this space of size nd, is very, very expensive. It's impossible. So what can we do? So we want to compress these features into memory, right? And the way to compress and what we want is that this compression should be linear. Why is this linear? It makes updating easy. Right? Because if you remember that we want to update the classifier constantly, right? And one of the ways of doing the update is by doing some kind of a gradient descent, for instance a stochastic gradient descent, that when you get a new email or a batch of emails with the user feedbacks on them, you just do a linear update on the you just do a gradient update on the classifier. Okay, ideally it should have guarantees, right, and should maintain sparsity as much as possible, right? That I don't want the emails themselves are obviously sparse data, and I don't want to densify it by too much. Okay, so how can we do this, right? So here is an obvious way. That suppose we create a hash table that hashes features into buckets, right? So what I mean is as follows: that suppose I have and this is my original set of features, right? Which essentially is very large, right? The dimension is very large, but it's sparse. So maybe I have some values out here, c plus 1 plus 2, and then plus 3, and so on and so forth. So this dimension is fairly large. Let me call it capital D. So what I could easily do is that hash it into a small number of dimensions, small d, right? So all that I need is that I need a hash function that goes from capital D to small d, right? And I can put it in here. Right? So basically, then a bunch of features can collide. So a bunch of features might go to the same position in the smaller smaller representation. And what I'll just do is basically add up, have a counter out here. That's the addition of these counts. So suppose these three features go into the same bucket in this using this hash function, then the value out here will be let me call this a1, let me call this ak, and let me call this ai. So the value out here is a1 plus ak plus ai, right? That's the value that you put in here, right? This could be one way of doing it, right? The question is that, is there a better principled way of thinking about this, right? Is this enough? Should I be doing something else? Right, and what about the guarantees? Because we were promising some bounds with the. We were promising some algorithms that comes with some guarantees. Right now, if you have paid attention in this course, it should not be very hard for you to realize that this is essentially sparse Johnson linear transformation, right? We were transforming from one particular vector to a smaller set, right, by using a hash function, right? Except that here we are using only a single hash function, right, instead of using multiple hash functions. So I could think of it as a hash function, as a hash transformation, or I could think of it as a random projection that preserves sparsity. Okay. So then in that case we should really take guidance from the principles of designing a random projection, as well as, and if we do this, we'll be able to draw upon the theoretical guarantees the random projection comes with, right, which we have seen is fairly strong. And in particular, one of the lessons that you should draw is that it's not enough to say, supposing this is again A1, AK, AI, and let's say all of these have gone to the same bucket. In particular, it's not enough to say to put A1 plus AK plus AI in the bucket, right? Because remember what sparse jail was doing. Sparse jail was adding a random sign to each of them, was multiplying each of them by a random sign. So I should do S1 times A1, let me keep this as it is. So instead I should do S1 times A1 plus SK times AK plus SI times AI, where each of the SIs is a binomial, is a Bernoulli plus minus 1 with probability half. Okay. So why is this important intuitively? Intuitively this is important because it helps the counts out here be unbiased estimators of the counts of the original set of counts. Okay, so this is one of the, and once we do this, we get exactly the sparse-Johnson-Lindenstrauss transformation with the with the sparsity one, and in fact we have seen this variant. This is what we call as a subspace projection, right? And we saw that it does preserve some very nice properties for the subspace preservation. Okay, so how do we use it in practice? Okay, so the algorithm seems fairly clear, right, in terms of the theory. So what do we do in practice? See, the theoretical guarantees, we assumed all independent hash functions, or at least some k-wise independent hash functions for some value of k. Typically k is like log 1 over delta, right, where delta, right? So in practice we don't really create k-wise independent hash functions by ourselves. What we do is that we typically use standard fast hash functions. There are deeper reasons for doing this as to why this should work. So people have thought about it, and there are some theoretical guarantees. But basically the idea is that given that the practical data is not entirely adversarially chosen, you don't really have to guarantee complete randomness, perfect randomness in your hash function. It's enough to choose a practical fast hash function. For instance, there's a particular software called Vopal Wabbit, right, that actually implements this. Gives you a very fast classifier using this feature hashing, and it uses something known as a murmur hash 3. And in fact you can a lot of APIs, standard API, machine learning packages have feature hashing as a standard API, including ones that including packages that run on scalable systems like Hadoop and Spark. Okay, so then given that ideally if you're using one of these machine learning packages, the suggestion is that you should definitely use the feature hashing API that they have provided. If you're using implementing your own classifier, you should use one of the standard fast hash functions like murmur hash, right? And this is what you typically do, right? That you create your let's say you're doing text classification, you create your you find out a representation of your document in terms of the n-grams, bigrams, etc. Then you hash your input data, and then you learn your classifier over this hashed space. Okay, so and when testing, we first hash the test point using the hash functions that we have used. So it's very important that you use the same hash functions that you use. You don't change the random seed, and then you apply the classifier. Okay, collision will happen. Of course, collision will happen, but that's exactly the point, that we are using these collisions. We are using these collisions to compress the set of features into a much smaller dimension, while preserving a lot of the geometry of the original set of data points. Right? And the kind of geometry that they preserve is what we have seen what Johnson-Lindenstrauss does, right? That it preserves more or less approximately the pairwise distance of the data points, and therefore if two classes are separable, it preserves the separability. Right? So this is the standard way of implementing it. Beyond this, you should use the domain knowledge. For instance, if you know that there are super important features that you don't want to collide with anybody, or there are groups of features such that you don't want this set of features to collide with this set of features, but maybe collisions among this set of features is fine, right? Then you should design your hash function you should basically partition your hash, the range of your hash functions in an appropriate way, right? And for all that you need to think carefully about the problem setting. Okay, so before we end, I'll show you a bunch of experimental results on for the spam classification from a paper that we had. This is a result that took 3.2 million emails from Yahoo's data and about 400 key users, right? So if we use the user personalization technique that I had mentioned, as well as the standard hash map, it would have taken us 70 terabytes just to store this. Right, because there happens to be around 40 times 10 to the 6 unique tokens in this data. Right, what we did was that we sort of used these hash functions in which we controlled the size of the hash space, right? And then we said that the hash space is only going to contain 2 to the 26 floats, and therefore the maximum size is 256 MB, right? And on the x-axis you see the number of bits in the hash table, and therefore the size of the hash table is 2 to the power of this, right? So this is 256 MB instead of the 70 terabytes, right? And on the y-axis we have plotted the relative classification error. Okay, that means that the black one is the baseline classifier, where there is a single classifier that's assigned to everybody, right? If we assign, if we happen to hash the classifier, that performance is obviously a little worse, right? But it soon boils down to the performance of the standard baseline classifier. If we assign everybody their own personalized classifier, we get a huge boost, more or less like 30%. 30% decrease in the error rate. Okay. Okay, so this is actually something that's very practical. So just to summarize, hashing has proven to be an important practical component in order to scale supervised machine learning to large feature spaces. Some amount of background theory for this is provided by the random projection literature, right? That this gives us the random projection literature gives us the intuition that what we're really doing is preserving the structure, the pairwise geometrical structure of the original space, and therefore it's useful in the supervised setting because the classes remain separable if they were originally separable. However, there's actually a lot of open questions. For instance, if the margin is large, how does that play a role in deciding the size of the target hash function, right? What about generalizability? What kind of generalizability bounds can we actually prove, right? Can I get? Do I really need the entire strength of the random projection, or can we sort of do with much smaller number of dimensions? So these are all questions. Does this generalize to nonlinear in the nonlinear setting, for instance? And these are all questions that people are pursuing for research. Okay, so the primary reference for this is a paper of ours that's called the feature hashing for large-scale multitasking learning, as well as the original paper that introduced hash kernels by Shi, Patterson, Rohr, Langford, Smola, and Strel, and Vishwanathan. Okay, that came out in AI Stats. And then finally, thank you.